So we're going to pick up essentially where we left off in the lecture on Wednesday. And the last thing we were discussing was curved mirrors. And we're going to look at the concave mirror situation first. Okay, so if I have a concave mirror and I have light coming in, and the light bounces off of that mirror, it's going to get reflected toward the center of curvature, right? So for the moment, we're going to assume that these curved mirrors are actually part of spheres, okay? So we would call these a spherical mirror. And when we have the bowl-shaped part of the mirror, which is doing the reflecting, then the rays are going to get reflected, and they're going to get reflected toward this common point. Now, why does this happen? Right, so if you recall, we said that light, when it bounces off of a flat surface, right, when light bounces off of a flat surface, the angles of incidence and the angle of reflection are equal, right? So the angles of incidence and reflection are measured with respect to this normal, right? And again, the normal means perpendicular. So if I have a flat surface and I draw an imaginary line that's perpendicular to that surface, then I can think of the angle of incidence and the angle of reflection as being symmetric about that imaginary line if I think of the rays meeting the surface and reflecting off of the surface right at the point where the normal and the surface meet, okay? And that principle can be extended to curves. Now here we don't have a flat surface, but the idea of the normal still holds. So everywhere along this curved surface, there's going to be a line that's perpendicular, but the normal is not always going to be in the same direction. So in this case, this normal is oriented here. Down here, the normal would be oriented this way, and the normals are going to point inward, right, off of the surface of the inner reflective surface of the mirror. And so that's the direction the light rays are going to get reflected, and they're going to be symmetric about the normal. So if I have a light ray coming in here and it bounces off of the mirror here, my normal is here, then the angle that this comes in with respect to the normal is also going to be equal to the outgoing ray with respect to the normal, okay? And the light rays get focused, or meet, if you will, at this point called the focal point. Now for spherical mirrors, and you can have different shapes, and we'll actually talk about a different shape here in just a moment, but for truly spherical shapes, there is a specific relationship between where this focal point is and the overall size of the mirror. So if we were to actually extend the mirror out and complete a full circle here, okay, if I were to draw that out and put a radius, okay, draw the center of the circle and then draw a line straight through here along the central axis, then the focal point would be halfway between the center of the sphere and the edge of the sphere, okay? So for a perfectly spherical mirror, the focal point is going to be half of the radius. Now what happens when we look at things in concave mirrors, okay? So as I mentioned in the lecture on Wednesday, one of the first things is that if I'm inside the focal point, so if my object, the thing that I'm looking at is inside the focal point, it gets enlarged. So if I place anything inside that focal point, the image that is produced is an enlarged image. And this is why makeup mirrors, for example, follow that design. If I flip the mirror over and I actually have my object over here and I'm reflecting the light off of the convex side of the mirror, then we can see that here a light ray, if I come in right here and it hits the mirror right where this normal is, then it's going to get reflected that way, okay? So in the concave case, the rays are going to converge, And in the convex case, the rays are going to diverge. I have a ray coming in down here. The outgoing ray is going to be moving downward. And here, the incoming ray is going to hit the mirror right here, and the outgoing ray is going to be reflected upward that way. So my reflected beams are going to be moving away from each other. So in that case, we say that we have a diverging mirror. And one of the consequences of this is for any distance from the mirror, my objects are going to appear a little bit smaller. And I also have a much wider field of view. I can see much more of what's going on in the room here than I can in this case. Now, where do curved mirrors find application, right? So one of the areas is rear view mirrors and other reflecting mirrors in stores like convenience stores or department stores for security reasons. And as far as a rear view mirror goes, the reason is, and I mean this is the reason for the other applications as well, but the rear view mirrors are probably the ones that most people are familiar with, or that people are best familiar with. So if I were to have a flat mirror, my field of view is going to be much more restricted based on the way that the rays can come in, hit off the plane, the flat surface, and then be reflected to my eyes to produce an image. Whereas with a convex mirror, I can see a much wider field of view. And so especially when you're driving and your car may be prone to blind spots visually, you want as much coverage with your mirrors as possible. And so this is why your rear view mirrors are of the convex design. And one more consequence of this, recall, okay, so for the convex case, my object is always going to be smaller in its reflected image than it is in real life, okay? For a flat surface, okay, the contrast that with a flat surface. If I have a flat mirror, then my image is going to be just as tall as the object. So when this woman is standing in the mirror and she sees her reflection, she sees somebody that is just as tall as she is. And not only that, but the person appears to be on the other side of the mirror just as far away as she is on her side. So everything is symmetric with flat mirrors, but not so with curved mirrors. In the curved case, if my image, with the concave case, if my object is inside the focal point, then it will be enlarged. What actually happens if I move beyond the focal point is it turns upside down. And in the convex case, it will always be right side up and the image will always be smaller. So this is why you have the warning on your rear view mirrors, objects may be closer than they appear, because if I just look at the reflected image, the object appears smaller than the object actually is. The image appears smaller than the object actually is. And so that's why we have that warning. Well, one application that curved mirrors find great and widely varied use in is astronomical telescopes. And the most modern designs involve what we call a primary mirror. That's the big mirror at the back of the tube. So at the front here, the major designs right now for the largest telescopes are that this end is open. There's not a lens up here, and the light is just allowed to come back, hit the mirrors, and then those mirrors bounce the light up to a secondary mirror, a very small mirror comparatively, and that mirror then reflects the light to the focus, where usually there is a camera or some sort of scientific instrument that then takes the light and collects the observational data. Now, one fundamental difference between most astronomical mirrors and the mirrors that we were just talking about is the shape of this curvature here. The shape of this curvature for astronomical telescopes is not spherical. It's actually parabolic. And the reason that it's parabolic and not spherical is a truly spherical mirror. The light coming in does not actually all meet at exactly the same spot. So these incoming rays can come in and bounce off the mirror, and they will actually not converge at exactly the same point. We call this chromatic aberration. And I'm sorry, spherical aberration. This one is spherical aberration. And so you can introduce fuzziness in your images and in your data if you use a perfectly spherical mirror, and you're going to get more fuzzy results than you would if you were to use a parabolic mirror. And most parabolic mirrors, we use slightly less curvature than spherical mirrors do, but they provide a more stable focus for the incoming light. So this primary mirror in the telescope here is actually going to be parabolic in shape as opposed to spherical in shape, right? And on top of that, right, there are ways that telescopes can be improved. And these two images are famous, very famous images from the mid-1990s. Well, early 1990s and then mid-1990s, from the Hubble Space Telescope. And when the Hubble was first launched back in the early 90s, there was a flaw in its optics with it actually concerning its primary mirror. There was a defect on the edge of one of the mirrors, and that defect caused extremely blurry pictures. And after a few years, NASA developed a workaround to correct the, they called it an astigmatism. They labeled it a telescopic astigmatism. And they developed a method to correct the optics without actually having to reinstall a new mirror. And they were able to produce a much sharper image. And the class of solution here for actually adjusting the light path of the light as it moves through the instrument instead of fixing the instrument itself is a class of solutions called adaptive optics. So ground-based astronomers, even though many telescopes that we have on the ground are much bigger than the Hubble, the main obstacle that they face is that from the atmosphere. So a lot of really large telescopes can take images close to this quality in terms of precision and resolution, but they're still very much limited by the atmosphere blurring the light. And that is where this kind of system of adaptive optics comes in, where there are parts of the optical system that can move, and they're computerized, and they move in accordance with a reference light beam, like a stable star in the field of view of the telescope. And these mirrors, these deformable rubber mirrors, are constantly moving up and down to adjust their positions to allow for the correct waveforms as the atmosphere blurs the light. This acts to try and undo that blurring, and you get a much sharper image at the scientific instrument as a result of these deformable rubber mirrors, which can oscillate. So in the next video, we'll look at a couple of think pair shares before we move on into refraction. But I hope that that particular video is useful to you, and we will see you at the next lecture. Okay.